Good morning. So today we will start the revision of grade 11 portions, that is paper 1 portions. We will start with chapter 2 vectors. So I will go a little bit faster because this is revision. And after completing the theory of the chapter, we will do some problems, because in vectors, even if you learn the theory, it's hard to solve problems. You have to interpret the problem in a proper way, only then solution is possible. So we'll quickly go through the chapter and then solve some problems. So what is meant by vector? Or before that, all physical quantities. Physical quantities are quantities which can be measured. For example, even length is a physical quantity because we can measure it. Time, then volume, area, and force. So all these quantities are physical quantities. And these physical quantities, which are measurable quantities, can be classified into two. Right? Which are they? The physical quantities can be classified into two. All of them. What are they? They are scalar quantities and vector quantities. So scalars and vectors. Now what is the peculiarity of a scalar quantity? Scalar quantities has only magnitude, while vector quantities has both magnitude and direction. This is the simplest way in which you can distinguish between a scalar and a vector quantity. Scalar quantities will have only magnitude. For example, if we tell length of a table is say 20 centimeter. So the 20 is the magnitude, centimeter is the unit. Now, for example, when we consider vector quantity, force is a vector quantity. If you are telling we are applying 20 Newton force in the downward direction. So if I am pressing this chair with 20 Newton force, that is in a particular direction. So 20 is the magnitude, Newton is the unit, and downwards is the direction. So can you tell me a few examples for scalar quantities? What are examples for scalar quantities? Speak up. Length, time,
energy,
what?
work,
Work, temperature, then what? Current. See, current has direction. Still, it is a scalar quantity, because for a vector, it's not enough that it has magnitude and direction. There is one more condition, that they should obey the vector laws of addition. Current doesn't obey vector laws of addition, so it's not a vector even if it has got both magnitude and direction. There are some quantities, special quantities like that. So current, note, it is a scalar quantity. Then you must have learned about magnetic flux and electric flux. So electric flux and magnetic flux are scalar quantities. Flux, phi. And then potential or voltage, electric potential or voltage. They are all scalar quantities. Now, can you give me some examples for vector quantities?
acceleration,
Displacement, yes,
displacement, then force,
velocity.
velocity. Yeah.
Then when you come to this electric magnetic things, electric field E. is a vector. Magnetic field B is a vector. So I'll mention here electric and magnetic fields. Field. Flux and potential are scalars, but field, electric field E or magnetic field B are vectors. Then what about area? Is it a vector or a scalar quantity? Area is a special kind of quantity. In physics, many cases we take area as a vector quantity. We have a tendency to consider area always as a scalar quantity, but in physics, we consider area as a vector quantity. Now, what is the magnitude? Magnitude is the actual area, length into breadth. Now, when you consider an area as a vector, we consider the direction of the area vector as perpendicular outside. Suppose this is the area. And if you want to consider this area as a vector, you will take its direction perpendicularly outwards. So area in many cases in physics are considered as vector quantities. So this is a special thing. Okay. Now, these are few examples for scalar quantities and vector quantities. And now we will learn more details about vector quantities. We will first learn few terms, few special kinds of vectors or few terms related to vectors. Then we will see how two vectors can be added. Because the way scalar quantities are added, we cannot add vector quantities. There are specific laws by which we can add vector quantities. That is why I said, as in the case of current, even if it has magnitude and direction, it doesn't obey the law of vector addition, so it's not a vector. So there are special laws for adding vector quantities, subtracting them, for multiplying them. So we will see all those things and also some operations on vector quantities, how to differentiate vector quantities, all those things we will see in this chapter. So a few terms related to vectors. Few terms related to vectors. Now let me just see how to represent a vector before that. How to represent a vector. Geometrically, we can represent a vector with a line and an arrow. And the line should have a length proportional to its magnitude. For example, I want to express a vector f. F is a force, so you can write it by the symbol f. And if it is a vector, to show it is a vector, we put an arrow mark above it. Suppose I have a force equal to 5 Newton. And this 5 Newton force is towards east. Okay, it's better to have an idea of the directions when we learn vector. So just have a direction of the idea of direction. You usually take this as east, this as west, this as north, this as south. So if I want to express a 5 Newton force towards east, I can write here like 5 Newton. Or if I want, this is a line with that arrow mark towards the east. Okay. Now I want to express another force. This is F1. Another force F2, which is 10 Newton towards south. Okay, so I have to express like this. I represented 5 Newton by this length. So when I express towards south 10 Newton, I have to take double that length, because the length of the line should be proportional to the magnitude. So I'm taking double that length and also putting towards the south. So this is 10 Newton towards the south. So you can represent a vector with the line and the direction towards which it is. Now, if you want to express another force for another vector, for example, velocity, a boat is moving northwest. So the velocity is equal to 2 meter per second northwest. Northwest means towards north and west, or they may directly give making 30 degree from the west towards north. So suppose it is making 30 degree north from west. So what I will tell, from west I will take around 30 degree and I can put 2 meter per second. So this is the velocity. So you have to note the direction and also the magnitude. So the length of the vector, when we represent, it will be proportional to the magnitude, and the direction should be given accordingly. So you need to have a sense of direction: east, west, north, south. And sometimes towards east, you can just make it a parallel to the x-axis. And towards south or north, you can make it parallel to the y-axis. But if it is making an angle with the north, with the south, or making an angle with the east, south, however it is mentioned, you have to take it like that. So this is how usually we represent a vector. And when we write, we represent a vector by a letter. Above that, there will be an arrow mark. Now, if you want to represent a vector in printing, it's very difficult to put an arrow mark above. So what people usually do is write the letter in bold. So if you find anywhere bold A in between the writing, you have to understand it's vector A. So in the normal font, if they are writing and one letter is kept in bold, which it means it's a vector. Is it clear to you how to represent a vector? Is it clear to you?
Yes, teacher.
Okay. Now let's go forward and see different kinds of vector or different terms related to vector. Sometimes you call a free vector and a localized vector. So a vector can be free or localized. Localized. Now, what is the difference between a free vector and a localized vector? A free vector means its starting point is not specified. For example, a wind is blowing. Wind is blowing with a velocity of 3 meters per second towards east. So you can draw that 3 meters per second here, or you can draw the same vector here. Okay, 3 meters per second. Or you can draw the same vector here. It doesn't matter where it starts. It's a wind towards east having velocity 3 meters per second. So it's called a free vector, which means its starting position is not localized, or the starting position is not fixed at any place. You can at any way shift it anywhere you want. You can freely shift it. Note that the length of the line and the arrow direction should remain same, and the starting position can be anywhere. So such vectors we call free vectors. But what is meant by localized vector? For example, I'm going to push this chair. I'm applying force on this chair in this direction. Okay, and saying another person is pulling it in that direction. So here we are applying force on a particular point. So you have to put the point specified. So you have to localize. For example, we usually represent vector along the coordinate axis. Suppose this is x-axis, this is y-axis, this is the origin. Now, at one particular point, more than two vectors are acting. For example, force is acting upon the handle of a box, a trolley box, and force is acting, one person is pushing it in one direction, another one is pulling it in another direction. So both the forces acts upon the same point, right? So there the forces or the vector is localized. So you can say that from the origin, suppose this is the handle of the box, you have one force acting towards x direction, say 2 Newton, another force acting in this direction, say 5 Newton. So both of them are acting at the same point. So you cannot take this 5 Newton anywhere else and row. It means it's localized, which means its starting point is fixed. So such vectors you call it is localized. Is that clear? What is free vector? What is localized vector? Is it clear what is free and localized vector? Okay, so let us move to another two kinds of vectors. Let me consider like vectors and unlike vectors. Like vectors means vectors which are in the same direction. And unlike vectors are vectors which are not in same direction. That's all. Whatever be the magnitude, it doesn't matter. So two vectors, suppose I have two vectors, for example, acceleration of 2 meter per second square, one vector, another vector, acceleration of 5 meter per second square, but both are in the same direction. So they are called like vectors. I have some force, say 2 Newton in this direction, another force, maybe 4 Newton in that direction, but suppose these two forces are in the same direction. So we call them like vectors. So all the vectors, whatever be their magnitude, if they are in the same direction, you call them like vectors. Now, if they are not in the same direction, you can call them unlike vectors. And unlike vectors, we usually tell they are not in the same direction, they are in opposite direction. Not in same direction, in opposite direction. They are in opposite direction. For example, two vectors are unlike. If this acceleration 2 meter per second square is in this direction and 5 meter per second square is in the opposite direction, you can tell them they are unlike vectors. They are in opposite directions. And here, similarly, 2 Newton forces in this direction and 4 Newton forces in the opposite direction. You can call them as unlike vectors because they are in the opposite direction. So like vectors means same direction, unlike vectors means opposite direction. Is it clear? Is it clear?
Yes, teacher.
Okay. Now another terms related to vectors. Vectors can be equal or opposite. So 3 and 4 are finished. So 5 and 6. 5 equal or opposite. So this is pretty clear from the words itself. Two vectors are equal if their magnitude and direction are same. For example, and are of the same kind. You cannot tell that 2 meter per second and 2 Newton. Even if they have the same direction and same magnitude, they are not equal because they are not of the same kind. So two vectors are equal if they have the same magnitude, same direction, and are of the same kind. So here 2 meter per second, this is also 2 meter per second. So they are equal vectors. So any two vectors, or suppose I have a vector A here, another vector B here, both having the same magnitude and same direction, they are equal and they should be of the same kind. Note that. Now, opposite vectors are two vectors having the same magnitude but opposite direction. Suppose a body is moving in this direction 3 meters per second and another body is moving in the opposite direction with the same velocity. So you can call that they are opposite vectors, or you can say one vector P is there, another vector Q, and they are in the opposite direction but having the same magnitude. They are opposite vectors. So a vector can also be called as vector A, vector B. There is another way to name a vector. For example, I have a line here, M, N, and this is the arrow mark. You can also call this vector Mn. Okay, so you can either name it as vector Mn or in this way as vector P, vector Q, doesn't matter. So suppose this is O, R. So you can name, this is in this direction, you can name this as OR, vector OR. So this is another way of naming a vector. Okay, is it clear to you what are equal and opposite vectors? Is
Yes,
that
teacher.
clear? Okay, now let me consider two another kinds of vectors which are called coplanar, collinear and coplanar. So let us consider 7 collinear vectors and coplanar vectors. Collinear means in the same direction. Coplanar means in the same plane. So co means in the same. So collinear means in the same direction. So collinear vectors, if you have a lot of vectors like this, see vector P, vector Q, vector R, vector S. So all of them, or T, vector T, so all of them are in the same direction. You call them, they are collinear vectors. Whatever be their magnitude, if they are in the same direction, you can also call them collinear vectors. Now, coplanar vectors. Coplanar vectors are vectors that lie in the same plane. So if I draw whatever on the whiteboard, it's all lying on the whiteboard, right? So they are in the same plane. For example, an ant. An ant is crawling on the surface of a table. So the ant can crawl from any direction on the surface of a table. So as long as it is on the surface of a table, its displacement is all coplanar vectors. So all vectors that lie on the same plane are called coplanar vectors. Is that clear? What is meant by collinear and what is meant by coplanar? Is it clear?
Yeah,
Colinear?
teacher.
Yeah, okay. Now, let me take another vectors. Vectors are called proper vector or null vector. So you can say 9 and 10. A vector can be proper. A proper vector or it can be a null vector. Now, a vector is called proper vector if it has a magnitude and direction. Suppose a vector force is equal to 20 Newton towards south. So it has a magnitude and a direction. So this vector is a proper vector and its magnitude is not equal to 0 and it has direction. So proper vectors have magnitude not equal to 0. So if the vector has magnitude not equal to 0 and it has direction, it's called a proper vector. Now, a null vector has its magnitude is equal to 0. And you will wonder about direction. It doesn't have a direction also. So why do we need a null vector? In case you want to add two opposite vectors. Suppose there is a force acting upon this. I keep this on my hand. So when I keep this on my hand, the weight of this crystal is acting downwards. And the reaction force offered by my hand, which is in contact with the crystal, is upwards. So when you add these two opposite forces, the result will be zero. But when you add two vectors, you should get a vector. So that zero should be represented by a vector, right? So we need null vector. So null vector is nothing but it has the magnitude zero and it doesn't have any direction. But whenever we need to add two vectors which are opposite, you will get a null vector. Or if you want to subtract two vectors which are equal, then also you will get the result a null vector. That's why we require null vectors. So these are few nomenclatures related to vectors. There is one more which is called a unit vector. So I don't have to put it with anything else. I'll put it as 11th term related to vector, a unit vector. Unit. So what will be such vectors? Unit vectors are vectors which have magnitude 1. So the peculiarity of unit vectors are that it has magnitude 1 and it will have direction. For example, if vector A has magnitude 1, suppose this is a force. So 1 Newton towards north. So you can represent with magnitude 1 and towards north. And usually we represent unit vectors with the cap. So a cap. You can represent the unit vector with a cap. Suppose I have another vector, vector P, which is equal to 10 Newton. 10 Newton, and it's in this direction. Vector P has 10 Newton. So you can also represent this vector P as equal to 10 in unit vector P, which means 10 is the magnitude and the direction is along the vector P. So usually we represent different vectors with their magnitude and a unit vector along with that just shows the magnitude. So unit vectors are vectors which has magnitude 1. When we express them, we usually express it as a unit vector with a cap on it or with a hat on it. Now, particularly important are unit vectors which we express along the x direction, y direction and z direction because it's the coordinate system. So when we consider the left hand coordinate system, this direction is the x direction. Up you have the y direction and the axis that comes out of the board, which I cannot show because I cannot draw anything 3-dimension on this board. I'm just representing it like this. It is Z. And conventionally, we consider the direction in the positive x direction as with a unit vector I cap. I cap means a unit vector along the x direction, and j cap means unit vector along the y direction, and z cap, k cap means a unit vector along the z direction. So I, j, k are 3 unit vectors along the x, y and z direction. Suppose I have a vector P which is equal to 3i. What does it mean? It means it has magnitude 3 and directed along the x-axis. Suppose I have a vector q which is equal to 4j. What does it mean? It means this vector has magnitude 4 and it's directed along the y direction. If I say I have a vector r which is equal to 3k, it means there is a vector having magnitude 3 and it's directed along the z direction. So this is how we represent the unit vector, and that's the usefulness of vectors. Now we will see not only along the x, y and z direction, you can take the combination of them and represent them in any direction. Suppose I have something here. I have something here. This is the origin, and you can represent this point by OT. So vector OT is equal to, suppose this distance is 2 and this distance is say 1, then I can tell 2y plus 1j or just j. So you can represent any vector with the combination of these unit vectors. We will come to it in more detail. We'll come to it in more detail later. So for the time being, I hope you understand what is meant by unit vector and what are I, j and k. Now let me ask you one thing. I have a vector b which is along the negative x-axis and it has a magnitude 4. How will I represent that? It's again along the negative x-axis and having magnitude 4.
-4.
-4, not finished.
I.
I. So you have to write it as -4i. So if I have another vector c, which is along the negative z-axis and having magnitude 5, how will I represent that? C is equal to
-5z.
-5, not z, k.
I. Okay.
K. Along z-axis, conventionally we take k as the unit vector. And so if you have another vector E, which is along the negative y-axis and having magnitude 6, how will you represent?
6y. -6y.
J. Don't forget the unit vectors along I, J and K means along X, Y, and Z. You cannot tell IX. You usually represent, this is the conventional letter. I means along x-axis, J means along y-axis, K means along z-axis. So you have to use IJK itself for the unit vectors. Now for special mention of two kinds of vectors. Oh, the time is going like anything. It's already time, right? I thought I will finish vector addition as well.